Namaste my dear students, welcome back to physics online class. In last class we have studied the concept of potential energy of system of two charges. We derived an expression for potential energy of system of two charges. Let us continue the discussion with the system of three charges. Potential energy of system of three charges. Okay. Now, in the last class we defined potential energy of system of charge. What is potential energy of system of charges? It is nothing but it is the total amount of work done in assembling the charges at their locations. Amount of work done in assembling the charges at their locations is called potential energy of system of charges. Now, let us consider three different points. Let P1 somewhere here, P2 and P3 be the three points in space. Okay. There is no electric field, it is just 3 points in space. There is no external electric field. Okay. Now we want to form a system of three charges. That means we have to assemble three charges at three different positions. Okay. Now, let us imagine that the charges Q1, Q2, Q3 are present at infinity. Okay, Q1, Q2, Q3 are present at infinity. Now we want to form the system of three charges. That means first of all I have to bring that Q1 to point P1, then Q2 to P2, then Q3 to P3, so that after assembling three charges in these three locations we will get the system of three charges. Okay. Now let us try to derive an expression for potential energy of system of three charges. Okay, let us start with the charge Q1. Okay. Now, first of all, or in the first step, work done in bringing Q1, amount of work done in bringing the charge Q1 from infinity to, I want to place that Q1, charge Q1 at P1, okay, point P1, Q1 to P1, let it be W1, amount of work done in first step be W1. This W1 is equal to 0. Why it is 0? Because we considered a space where there is no external electric field. If there is no external electric field, there is no opposition for, if you try to move this Q1 from infinity to point P1, there is no opposing force. Electrostatic force is not there, or electric field is not there. Since there is no electrostatic force or opposing force, external force is not necessary to bring this Q1 from infinity to point P1. So force is not necessary. If force is not necessary, we know that work done is equal to 0. So with the help of amount of work done W1, which is equal to 0, we shifted the charge Q1 from infinity to point P1. Now Q1 reaches here, so at P1, now Q1 is there. We placed the charge Q1 in the first step. Okay, what is the next step? In the second step, we have to move the charge Q2 from infinity to point P2. Q2 from infinity to point P2, same as previous derivation. Now, after placing Q1, we know that a charge produces electric field in its surrounding region. We placed Q1 here. This Q1 will produce electric field in its surrounding region. Okay. Now if you try to move this Q2 from infinity to point P2 or anywhere inside the electric field produced by Q1, that charge will experience electrostatic force. Depending on the polarity, if Q1 and Q2 are like charges, there will be repulsive force. If Q1 and Q2 are unlike charges, there will be attractive force. Totally, when you try to move that Q2 from infinity to anywhere inside this region, due to electric field, that Q2 experiences electrostatic force. Now, we want to place that Q2 here, that is at point P2. Before bringing that, let us calculate the potential at this point. What is potential? Potential is nothing but it is the amount of work done in moving unit positive charge from infinity to point P2. Now, at the point P2, potential, electrostatic potential due to Q1. Now Q1 is there, it produces electric field. Inside the electric field we know that potential will be there. So point P2 lies inside the electric field of Q1. It is at finite distance. So produces electric field. Potential at point P2 is given by, we know the expression for potential due to a point charge. I'll represent the potential as V. V is equal to 1 by 4 pi epsilon naught, 1 over 4 pi epsilon naught into, now the charge is Q1 divided by, let the distance between these 2 points P1 and P2 be R12. Okay, separation between point P1 and P2 be R12. Then I can write it is equal to Q1 divided by R12. This is potential at point P2, potential at point P2 due to Q1. Okay. That means if you want to bring a unit positive charge from infinity to point P2 against the electric field produced by Q1, this much amount of work has to be done. Okay, V is the amount of work done required. Now the second step, okay, second step, work done in bringing, now which charge? Work done in bringing charge Q2 from infinity to point P2. We want to place that charge at point P2. Amount of work done in bringing, work done in bringing Q2 from infinity to point P2 is given by W2. I'll represent it as W2. To bring unit positive charge, amount of work done is V. Now we want to bring the charge of magnitude Q2 from infinity to that point. We know the relation between electric potential and work done. Now this W2 can be written as magnitude of charge Q2 multiplied by potential at this point. Potential where we want to place the charge, or where we want to place the charge Q2. So Q2 into potential at that point is V. So that is equal to Q2 into V. So that is equal to, or W2 is equal to, substitute the expression for V. Now it becomes 1 over 4 pi epsilon naught Q1 into Q2. So I can directly write Q1 into Q2 divided by separation between the charges, that is equal to R12. Okay, R12. Work done in bringing first charge W1 is equal to 0 because there is no external electric field. Work done in bringing second charge is equal to 1 by 4 pi epsilon naught Q1 Q2 divided by R12. This is because first charge produces electric field. Against that electric field, work has to be done in bringing the second charge from infinity to point P. Okay, sorry, point P2. Now P2 reaches here, Q2 reaches the point P2. So system of two charges is formed. If you want to calculate the potential energy of system of two charges, just add these two expressions, W1 plus W2, amount of work done in assembling the charges. Okay, now third step. So before third step, now let us consider point P3. Point P3. At point P3, Q1 produces an electric field is due to, at point P3, two electric fields will be there. One is due to Q1 and another one is due to Q2. That means at this point we will have two potential values. One is due to Q1 and another one is due to Q2. Isn't it? So at point P3, what is the net potential, or what is the total potential? Total potential is nothing but it is the sum of potential produced by Q1 and potential produced by Q2. Now let us consider the point P3. At P3, okay, first of all, potential due to Q1. Let the separation between the point P3 and Q1 be R13, and let this separation be R23, R23. Okay, at point P3, potential due to Q1, I'll write it as V1 is equal to 1 by 4 pi epsilon naught. Potential at this point, we are calculating the potential at this point, 1 over 4 pi epsilon naught into, due to Q1 potential is produced, therefore charge is Q1 divided by separation between these two now, okay, these two, that is equal to R13, okay. 1 over 4 pi epsilon naught Q1 divided by R13, potential due to Q1. At the same time, at the same point, now at P3 only, potential due to, see, Q2 also produces electric field, therefore due to Q2 there will be a potential due to Q2. Okay, at P3, potential due to Q2 is given by, let it be V2. V2 is equal to 1 over 4 pi epsilon naught into Q2 is the charge. Now this charge, due to this charge Q2 divided by distance from the charge to the point is R23, therefore it is divided by R23. Okay, V2 is equal to 1 by 4 pi epsilon naught Q2 divided by R23. Now this is the potential at point P3 due to the second charge. Now therefore net potential at point P3, I'll represent it as V1, 2, that is potential due to two charges Q1 and Q2. V1, 2 is equal to, we know the superposition principle, at any point net potential is the algebraic sum of potential due to each charge. Now potential due to first charge is V1, potential due to second charge is V2, therefore adding those two values, 1 over 4 pi epsilon naught Q1 divided by R13, that is V1, plus 1 over 4 pi epsilon naught Q2 divided by R23. This is the expression for net potential at point P3. Okay, net potential at point P3. Now, net potential at point P3 is equal to V1, 2 means if you want to bring a unit positive charge from infinity to point P3, under this situation, this much amount of work is needed. Okay, this much amount of work has to be done in shifting unit positive charge from infinity to point P3. Now what we want to do? We want to shift a charge of magnitude Q3 from infinity to point P3. That is our third step. So third step, work done. Okay, third step, work done in bringing Q3 from where to where? From infinity to point P3. We want to place the charge Q3 at point P3 to form the system of three charges. So therefore work done in bringing Q3 from infinity to point P3 is given by, I'll represent it as W3. W3 is equal to, we know the relation between work done and potential. We used the same relation here. Now at point P3, we want to place charge of magnitude Q3. Therefore Q3 into potential at this point. Potential at this point is nothing but V1, 2. So V1, 2. So that is equal to, okay, that is equal to Q3 into 1 over 4 pi epsilon naught Q1 divided by R13 plus 1 over 4 pi epsilon naught Q2 divided by R23, that is V1, 2 is work done. So therefore W3 is equal to, amount of work done is equal to, multiply by Q3, 1 by 4 pi epsilon naught Q1 into Q3 divided by R13 plus 1 by 4 pi epsilon naught, okay, 1 by 4 pi epsilon naught Q2, this one, into Q3. So Q2, Q3 divided by R23 is the total amount of work done in moving Q3, the charge Q3 from infinity to point P3. So now Q3 reaches here. Okay, with these three conditions, we placed, using these three conditions, we placed Q1, Q2, Q3 at their locations. Okay. Therefore, potential energy, the definition of potential energy of system of two charges says that work done in assembling the charges at their locations itself represents potential energy. So to bring Q1, W1 is the amount of work done. To bring Q2, W2 is the amount of work done. To bring Q3 from infinity to that point, W3 is the amount of work done. Therefore, total work done in assembling the charges. I'll write here. Okay. I'll write here. So total amount of work done in placing three charges at their locations, W is equal to W1 plus W2 plus W3. Now this is the total amount of work done or net work done in placing those three charges. So that is equal to, so that is equal to W1 is 0, no need to write here, W1 is 0, W2 is 1 by 4 pi epsilon naught Q1 Q2 divided by R12, okay, so W1 is 0, plus W3 is 1 by 4 pi epsilon naught Q1 into Q3 divided by R13 plus W3 is, plus 1 over 4 pi epsilon naught Q2 into Q3 divided by R23. So W1 plus W2 plus W3 is equal to this much, out of which W1 is equal to 0. This part represents W2, this part represents W3. So therefore, total work done is equal to, or W is equal to this much. So by definition of electric potential energy, this amount of work done is stored as potential energy. Therefore, straight away I can write potential energy U is equal to 1 by 4 pi epsilon naught Q1 Q2 divided by R12 plus 1 by 4 pi epsilon naught Q1 Q3 divided by R13 plus 1 by 4 pi epsilon naught Q2 Q3 divided by R23. R12, R13, R23. Okay. If you want, one more step is possible. U is equal to, you can take 1 by 4 pi epsilon naught outside into Q1 Q2 divided by R12 plus Q2 Q3 divided by R23 plus Q1 Q3 divided by R13. This is the final expression for potential energy of system of charges, system of three charges, total amount of work done. If there are n number of charges, if you want to find the potential energy of n number of charges, what will be the expression? If there is one more charge, for example, if you want to get the system of 4 charges, Q1, Q2, Q3 and Q4, then this equation will be Q1, Q2 divided by R12, Q2, Q3 divided by R23, Q1, Q3 divided by R13, then it continues like this, okay, Q3, Q4 divided by R34 and so on. Okay, now this is the expression for potential energy of system of 3 charges. I think it is clear. Definition of potential energy of system of charges, work done in assembling the charges itself is the potential energy. In forming the system of 3 charges, work done in bringing first charge is 0 because there is no external electric field. Work done in bringing second charge, that is done against the electrostatic force produced by first charge, therefore this is the expression. Work done in bringing the third charge, that is done against the electric field produced by first 2 charges Q1 and Q2, therefore work done is this much. So total work done is given by this expression. By definition, potential energy is equal to work done, therefore potential energy of system of 3 charges is given by this expression. Okay, I think it is clear. Okay, let us move further. Now based on this concept, that is potential energy of system of charges, let us solve two simple problems. Okay, simple problems. So first one here, two positive point charges 16 nanocoulomb and 12 nanocoulomb are 10 centimeter apart in air. 2 point charges are given, 16 and 12 nanocoulomb. Separation between the charges is also given, it is equal to 10 centimeter. Calculate the work done in bringing them 4 centimeter closer. Those two charges are separated by a distance of 10 centimeter. If you want to bring those charges 4 centimeter closer, that means if you want to reduce the separation between the charges by 4 centimeter, what is the amount of work done in that process? That is the question. Okay. To solve this problem, remember the concept of conservative force field, or remember the point related to conservative force field, that is, in case of conservative force field, work done results in change in potential energy, or work done is equal to change in potential energy. That concept we have to use because electrostatic force is conservative in nature. Now let us consider the first case. Charge 16 nanocoulomb, it is given that positive charges 16 nanocoulomb and another one is 12 nanocoulomb. 12 nanocoulomb are separated by a distance of 10 centimeter. Distance between these two is equal to 10 centimeter. Okay. Now it is the system of two charges. There is no external electric field or nothing. So system of two charges. For this configuration, we can calculate the potential energy using the formula. Potential energy of system of two charges is given by 1 by 4 pi epsilon naught Q1 Q2 divided by R12. Okay, we can calculate the potential energy using this formula because it is a system of two charges. Next, after bringing these two charges 4 centimeter closer, that means for new configuration, once again we can calculate the potential energy using the same expression. If you find the difference between those two potential energies, then according to the concept of conservative force field, the difference in the potential energy itself represents the amount of work done, isn't it? So difference in potential energy itself represents the work done in bringing the charges 4 centimeter closer. So now for this case, potential energy, I'll write here, potential energy of this system, I'll write it as Q1 for in first configuration. Q1 is equal to, reference equation is U is equal to 1 over 4 pi epsilon naught Q1 Q2 divided by R12, that is potential energy of system of two charges. So potential energy for this position, substitute the values. 1 by 4 pi epsilon naught, we know the value of 1 by 4 pi epsilon naught, that is 9 into 10 to the power 9 into Q1 is now 16 into 10 to the power minus 9 nano it is. So 16 into 10 to the power minus 9 nanocoulomb into Q2 is 12 into 10 to the power minus 9 divided by 10 centimeter is the separation, that is 10 into 10 to the power minus 2. Okay, 10 centimeter is the separation between the charges, 10 into 10 to the power minus 2. Now calculate the values or find the answer for this is equal to 9 into 16 into 12, that is 192 into 10 to the power plus 9, 10 to the power minus 9 cancels, Here 10 to the power 1, 10 to the power minus 2, that means it is 10 to the power minus 1 here. If you take that 10 to the power minus 1 here, it becomes 10 to the power plus 1. So remaining is 10 to the power minus 9, that is this one, into 10 to the power minus 1. If you take it here, it will becomes 10 to the power plus 1. So multiply the values. Then 1728 into 10 to the power minus 8, it is potential energy, therefore in terms of joule, expressed in terms of joule, this is the amount of work done. U1 is equal to this much. Sorry, not work done, it is the potential energy. It is right, 18. Yes, 1728 into 10 power minus 8 joule. Let us consider the second case. Amount of work done in bringing the charges 4 centimeter closer. Initial separation is 10 centimeter. If you bring those two charges 4 centimeter closer, not the separation between the charges is equal to 4 centimeter. 4 centimeter is the moment, that means new separation will be 10 minus 4, that is equal to 6 centimeter. That means in the second case this will be the condition. The charges 16 nanocoulomb, 12 nanocoulomb. Separation between them is 4 centimeter closer, so remaining will be 6 centimeter. 6 centimeter is the separation between the charges. So now for this configuration, potential energy, let us calculate the potential energy of system of two charges. Potential energy, let it be U2 is equal to, again same formula, 1 by 4 pi epsilon naught is 9 into 10 to the power 9 into first charge is 16 nano, 16 into 10 power minus 9 into 12 nano is the second charge, that is 12 into 10 to the power minus 9 divided by, now the separation between the charges is equal to 6 centimeter, 6 into 10 to the power minus 2. Okay, 6 into 10 to the power minus 2 is the separation. Now this is equal to 10 power minus 9, 10 power minus 9 cancels, 6 once, 6 2 times, okay, 6 2 times. So that is equal to multiply this, 9 into 16, that is 144, 9 into 16, or I'll write one more step, 9 into 16 into 2, 9 into 16 into 2 into 10 power minus 9, this one 10 power minus 9 divided by 10 power minus 2 is there. If you take it into numerator, it becomes plus 2, so 10 to the power 2. In the denominator 1 is remaining, no need to write that, is equal to 9 into 16, that is 144, into 2, that is 288 into, okay, 288 into 10 power minus 9, 10 power plus 2, that is equal to 10 power minus 7 joule. Okay. So for the new position or new configuration, potential energy of system of these two charges is equal to 288 into 10 power minus 7 joule. Now, what is the work done? We have to calculate the amount of work done in bringing those two charges 4 centimeter closer. For that, use this concept. In case of conservative force field, work done is equal to change in potential energy. So that is equal to final potential energy U2 minus initial potential energy U1. Substitute the values. See here, it is in terms of 10 to the power minus 8. Here it is in terms of 10 to the power minus 7. To find the difference between those two values, let us change this one. It is equal to 2880 into 10 to the power minus 8 joule. isn't it? I added one position here, 10 to the power minus 7 becomes 10 to the power minus 8. So that is equal to 2880 into 10 to the power minus 8 minus 1728 into 10 to the power minus 8. So that is equal to U2 minus U1 is equal to 2880 into 10 power minus 8 minus 1728 into 10 to the power minus 8. That is equal to, now the difference here it is 2, 7 minus 2 5, 8 minus 7 1, 2 minus 1 1. Okay. Yes, into 10 to the power minus 8 is there, minus 8. So that is equal to W. Work done in bringing those two charges 4 centimeter closer is given by this expression. This work done is equal to this much, 1152 into 10 to the power minus 8 joule. Yes, okay. So this is the equation to calculate the work done. Change in potential energy is the work done, and this is to calculate the potential. For first configuration, this is the potential energy. For second position, this is the potential energy. Difference between these 2 points represents potential energy, which is nothing but potential difference. Okay, I think it is clear. Okay, let us solve one more problem. Yes. This one is very simple problem. Calculate the work needed to place 3 charges, 2 millicoulomb, 3 millicoulomb and 4 millicoulomb. All are the positive charges at the 3 corners. There is a small mistake here. At the 3 corners of an equilateral triangle of side 3 centimeter. So work needed to place 3 charges at 3 corners of an equilateral triangle. That means, what is the amount of work done in forming system of 3 charges? That is the question. Equilateral triangle with the side 3 centimeter, here also 3 centimeter, here also 3 centimeter. At one corner we want to place 2 millicoulomb charge, plus at another corner 3 millicoulomb charge, and at another corner 4 millicoulomb charge. What is the amount of work done? So work done is nothing but, we know that work done in case of assembling the charges itself represents the potential energy. Therefore we can use the expression for potential energy to calculate the work done. So W is equal to, it is the system of 3 charges, 1 by 4 pi epsilon naught into Q1 Q2 divided by R12 plus Q2 Q3 divided by R23 plus Q1 Q3 divided by Q1 Q3 divided by R13. Using this formula we can calculate the work done, which represents potential energy of this system of charges. Substitute the values, 9 into 10 to the power 9 into Q1 into Q2, Q1 is 2, 2 into 10 to the power minus 3 into Q2 is 3, 3 into 10 to the power minus 3 divided by, separation between the charges is side length of the side, that is 3 centimeter, 3 into 10 to the power minus 2. Remember this condition, while using any while calculating any values, the distance must be in terms of meter, in terms of SI units, that's all. Plus Q2 3 into 10 power minus 3 milliliters into Q3 4 into 10 power minus 3 divided by 3 into 10 power minus 2 plus 4 into, or Q1 Q3, that is 2 into 10 power minus 3 into 4 into 10 power minus 3 divided by 3 into 10 power minus 2. Okay, so that is equal to 9 into 10 to the power 9. Okay, see here 3 into 10 power minus 2, 3 into 10 power minus 2, 3 into 10 power minus 2, I can take it outside. 3 into 10 power minus 2 into 10 power minus 3 into 10 power minus 3. It is equal to 10 power minus 6, which is there in each term. Therefore, I can take it outside. Minus 10 to the power minus 6. 3 into 3, minus 3 into minus 3, minus 6, minus 3, minus 3, minus 6. In each term, there is 10 power minus 6 into 2 into 3, 6, plus 3 into 4, 12, plus 2 into 4, 8. Okay. So simplify this. Simplify. What we get is 3 ones, 3 times. So that is equal to 3 into 10 power 9 into 10 power minus 6. This minus 2, if you take it on into numerator, it becomes 10 power plus 2 into 8 plus 12, 20, 20 plus 6, 26. That is equal to 26 into 3, 78, 78. 10 power plus 9 plus 2, that is 10 power 11, minus 6, that is 10 power 5. Okay, 10 power 5 joule. This is the amount of work done in placing 3 charges at 3 corners of an equilateral triangle of side 3 centimeter. Actually, this quantity itself represents the potential energy of this system. Okay. If it is asked to calculate the potential energy of system, you can use the same formula and same calculation, you will get the same answer. Okay, that is the potential energy. Okay, next see, in this problem we calculated the work done or potential energy of system of 3 positive charges. If any one of the charge is negative, or if any 2 or all the charges are negative, then what will be the difference? Difference will be in this substitution. If this is negative, then this term will be positive, this term will be negative, because here instead of 4 we have to substitute minus 4. Okay, you will get negative potential energy. Again, the procedure is same. Add the values. If it is negative, subtract the values, you will get the final answer. That means this equation is applicable in case of positive charges or negative charges, or in case of any system. Okay, I think it is clear. Okay, next, I'll stop the discussion here. In the next class, let us consider the concept of potential energy of system of charges in the presence of external electric field. What we derived in previous class and this class is in the absence of external field. In the next class, let us consider the concept of potential energy of system of charges in the presence of some external field. Okay, thank you so much.